Good morning, everyone. Thank you so much for joining us today. I'm hoping you're having a great time here in Atlanta. My name is Anya Kramar. I'm a software engineer at Red Hat. I've joined Kubeflow community just in the beginning of this year and I've been really enjoying it so far, working with all of you. And I've been contributing to the open source projects. One of them is Kubeflow SDK, and I'm really excited to talk about that today. I'm here with my colleague, Anthony. Do you want to introduce yourself?
Thanks, Anya. So my name is Antonin. Welcome to this presentation. I'm one of the many maintainers for the Kubeflow SDK and the Kubeflow trainer. And as Alex said, I also feel I'm not very much qualified for it, but I can feel the responsibility. And I'm also a software engineer at Red Hat, working on OpenShift AI, where we use the Kubeflow SDK and the Kubeflow trainer for LLM fine-tuning and also distributed model training. And I'm very excited to be here to share what's new in the newer version of the Kubeflow SDK.
Thank you. Before we stand in, I'm curious, I just want to see who is in the room. Just a quick show of hands. How many of you have tried to use the SDK of any Kubeflow project? Please raise your hand. Okay, quite a bit. And have you tried to use multiple of them in the same time, like Kubeflow Trainer with Katib or Model Registry with pipelines? Okay, so we've got a few people who are quite familiar with the landscape we will be talking about today. But for those who are not, no worries, we'll walk through everything together. So, let's imagine I'm an AI practitioner and I have a goal. I want to run my AI workloads at scale with Python. And when I say at scale, I mean I want to run any kind of AI workloads like data processing, training, fine-tuning, hyperparameter optimization. And I want to start doing that locally on my local machine. And then whenever I need to, I want to scale it and distribute it across multiple nodes and GPUs. And I want to stay and do that in my Jupyter notebook using Python. No need to learn any Kubernetes at all. So, sounds like a great plan, but let me show the reality. So this is what you would face today, actually. The first one is Kubernetes expertise required. So to build any AI workload on Kubernetes, you have to know Kubernetes. You have to know what is pod, what is PVC, what is CRDs, etc. But the issue is that I'm an AI practitioner, and generally, I don't care about all of that. I care about my model, about what hyperparameters give me the best results, etc. But I have to become an infrastructure expert just to build and run AI on Kubernetes. And on top of that, we have a slow iteration loop. So, for example, I do train my model on Kubernetes. I scale it. And then I found out that there's a bug in my training function. Sorry. Yeah. What do? I have to rebuild my Docker image, then wait a few minutes, push it to the registry, update my YAML files. I have to kubectl apply, and so on. And then I found another bug, and I have to go over it all over again. And then if you want to use Kubeflow projects today, you have to install different APIs, separate projects. Each of them has different installation, like Kubeflow Trainer, KFP, Katib, etc. And all of them, they have different APIs, and you have to learn how to deal with them to understand what APIs belong to what project. And then on top of that, there's version incompatibility issues. You spend hours to try to understand what Kubeflow Trainer works with what version of Katib, or what version of KFP works with my cluster, etc. So all of these issues are a big barrier for AI practitioner to just run any AI workload on Kubernetes. So we step back and ask ourselves, is there a better way to do that? And the answer is yes. Introducing Kubeflow Unified SDK. Unified SDK, it's a set of unified Python APIs that let you run any type of AI workload at scale, at any scale. So this is one package that you install, pip install Kubeflow. You can do that today. We have just released Kubeflow version 0.2 recently. So as you can see, Kubeflow SDK sits in the middle. It's a unified interface layer between you, AI practitioner, and all of the Kubeflow project. So you can run any AI workloads like Kubeflow trainer with training model, fine-tuning, then hyperparameter optimization, etc. You have a unified set of APIs. You don't need to learn any new APIs. No Docker, no YAML files. It's straightforward, all the same APIs, only Python within your Jupyter notebook. And then what is really important is that we have a cool feature that you can start doing that locally on your local machine and then scale it anytime you need to and distribute it across different nodes and GPUs. So where we are today, we have a training and fine-tuning capabilities. Can you hear me? Yeah. Capabilities and then hyperparameter optimization available today. You can use that from now. And then we have a clear roadmap that Antonin will talk about later on. So let me show you the demo now. So I'm going to take you to here. What I'm going to do is I will be using my Kubeflow SDK, and I will train my CNN function on the fashionist dataset. And then later on, I will do my hyperparameter optimization. And let me get started. So to do that, I first install my Kubeflow, pip install Kubeflow, really easy. And then I define my training function. So this is just a PyTorch code. Here's my CNN, just few convolution layers. Then I set up my PyTorch distributed. I download my fashionist dataset, and that's it. Over here I have my training loop over a few epochs, and I calculate my loss and accuracy over here and print it out. So I run that, and then to do my distributed training, I use trainer client, which is available in Kubeflow Unified SDK. I just import that and initialize my trainer client, really easy. The next step is I need to choose a training runtime. So training runtimes is the runtime that is predefined by platform administrations and contains all of the infrastructure details that as a AI practitioner I don't care about. So I just can, using this API, I'll list runtimes. I can see all of the runtimes that are already existing over here on my cluster, and I'm choosing Torch distributed. That's it. After that, to run my distributed training, I'm just using one API train. And to do that, I create the train job template. So this is the template that I can create and reuse it for training, fine-tuning, hyperparameter optimization. To create that, I provide my runtime and then the function that I previously defined. I also provide the arguments that I'm going to train on. So this is learning rate and momentum. And then to do the distributed training, I specify this parameter, which means I will distribute my training across two nodes. Each of them will contain one GPU. And to start my training, I just use one simple API train. And that's it. As you can see, the train job has been created. We can see the steps. So using this API list jobs, we can see that all of these, so we have a few jobs that are created, and this one that I just created, this is running. And previously I have created two more train jobs that are already completed. Then we do while I was talking, it's already completed, not running, so let me remove that really quick. Yeah, so now it's already completed. I'm using wait for job status. The job is already in run and completed. We can see that our job using get job API, we can see that we have a distributed training over here. We distributed across 2 nodes. One of them, each of them has 1 GPU. And then we can see the logs of our training in real time using this simple API get job logs follow through. We can see that our loss is decreasing and accuracy is increasing with every step, every epoch. And this is final loss, 0.41. Now I'm curious whether I can do the hyperparameter optimization, and we can do that with Unified SDK. To do that, I'm using Optimizer client, and super simple, I use Optimize API. I provide the train job template that I previously already defined, and I'm reusing that for hyperparameter optimization as well. I provide the trial config where I'm saying that, okay, I want to use I want to have 10 trials, meaning that Optimizer will create 10 train jobs and choose the best one for me. And I want to allow 2 parallel trials running in the same time. I also provide the search space, which is learning rate and momentum. So I'm saying, okay, those are the hyperparameters that I want to optimize. And I define the parameters, the set of parameters that I can choose from. And then the objectives that I want to optimize my model is, I have 2 of them, and the first one is loss. I want to minimize loss and then maximize accuracy. Currently, it will choose the first one, and it will optimize on the loss. And then when I run that, so super simple, I just using one API optimize, and it creates my optimization job. We can list jobs. As you can see, I'm using the same API as in trainer client. We can see that one optimization job has been created. Currently, there are no trials, but we can wait for job status until it's running. And we can see that currently it's already running, and we have 2 trials, meaning 2 train jobs running on our cluster, and with this set of parameters. Now I'm using GetJob logs to see the logs in real time from our train job with the set of hyperparameters, as you can see, and then it also provides the metrics. Cool, and now I'll take you to the cool part, which is the UI. So this is the Katib UI. Let me choose. Yep. This is my Katib UI that we use for hyperparameter optimization. As you can see, we have one optimization job over here that has been created 1 minute ago. I open it up and I can see a beautiful graph which represents those trials. Each of them are the train job that is created. We have learning rate, momentum, accuracy, and loss. This is our metrics, and then those are hyperparameters with different values. And you can compare them. You can see this one is doing the best regarding loss. And we can go down over here and we can see the list of the trials that are created. Those are already completed, and those are running right now with a set of parameters, so you can compare really easy. With the yellow color, it provides the current best train job hyperparameters they can choose, and you can see the values over here. We can open it up and we can see how our model was doing within time. So really cool. And then if I go back, let me see. Yeah, now all of these trials are completed. And when I go back, I can see the best results here. And it provides the learning rate and momentum, and then also the loss, which is 0.3. And before that, if you remember, it was 0.4. So super easy, it's just Python, no Kubernetes needed, no YAMLs. And I wanted to show you one cool thing is that, you remember when I was talking about if I have a bug in my code, what do? Rebuild the image, update the YAML file, kubectl, apply, etc. So I just want to emphasize on how super easy it is. So let me just comment out this import and see what happens. So I set my train function, and I create my new train job over here, and then let me go to I'm using get job logs to see the logs, and you can see the issue in your logs already, and you just go back, fix that, and everything is supposed to be working now. Yep. I submit the new train job and do get job logs here. And now it's working. So super easy. And you don't need to rebuild any images. You don't need to understand Kubernetes at all. You just use Python, stay in your Jupyter notebook. And on this note, I pass it over to Antonin.
Thank you, Anya. It's fantastic. So I think we can take a quick moment to see how that all works under the hood. So Anya just showed the client side of things for the data scientist, the AI experts persona. And now we are going to look at a bit more detail on the backend side in Kubernetes for those of you that might be interested in more the MLOps side of things. So it all starts when you create a train job template or train job with some parameters and some function, training function. Then using the Kubeflow SDK, you're going to call the train method using that train job template. And that's going to create a train job resource in Kubernetes. And in that train job resource, there is a training runtime that's being referenced that's used by the Kubeflow trainer to retrieve additional parameter for the training job. For example, the container image that's used to run the training job, etc. And the Kubeflow trainer combines all the parameter from the training runtime and the train job in a resource that's a job set resource. So the job set API, it's a very powerful API that Kubernetes provide to define a set of coordinated jobs. So for example, you can have 2 jobs running in parallel to download the pre-trained model, for example, when you run a fine-tuning job and the dataset, they will run in parallel, and when they are all completed, then the actual training job, fine-tuning job can go on. And once you've tested that your train job works correctly with a set of fixed hyperparameter, then you can run your hyperparameter optimization experiment. So for that, you use the optimizer client and you call the optimize method using the train job template you had created previously. And then you configure a few things related to hyperparameter optimization, some configuration with respect to the parallelization, the source space for the hyperparameters, and the objective function and the algorithm as well. So once you call that method, the Kubeflow SDK is going to create a optimization job resource. Katib, which is the HPO controller, is going to deploy the algorithm service for the one that's configured for the experiment. So that can be HyperOpt, Optima, and Scikit Optimize, I think, which are supported out of the box. But it can be also bring your own HPO algorithm if you want. With that algorithm service deployed, Katib is going to request a set of suggestions for the hyperparameters. And the algorithm service is going to provide that combination of hyperparameter. And for each of those suggestions, Katib is going to create a trial, which is a resource that's going to keep track of each run for the experiment. And the Katib is going to create ultimately a train job that the Kubeflow trainer is going to run. And once the train job are completed, the result is fed back to the algorithm service, and the best trial is picked up, and you get the optimal result for your experiment. And so that's about it for the that's new functionality, the optimizer client that's been added into the latest version of the Kubeflow SDK. There is another main focus that we've introduced for that newer version, which is the local execution mode, where you can actually run your train job locally and then run them on Kubernetes without any code changes to your training logic. So for that, we've developed two what we call local runtime backends. The first one is based on Python subprocesses. So your train job are going to run as processes. And for each of them, the Kubeflow SDK create an isolated Python virtual environment. So your dependencies are isolated and you don't have any conflict. So that's the backend that is the easiest to use because you basically don't have any prerequisite. You can pip install the Kubeflow SDK and then you can run your train job. But that easiness comes obviously with a few limitations. The one is that conceptually it doesn't have access to the container runtime information, if you want. So you only have support for one specific hard-coded runtime, which is the PyTorch distributed runtime. So you cannot reuse like any other supported training runtime. And it only supports a single node mode. So you cannot do distributed training job using that local process runtime. You can still use GPUs if you want, but you'll have to be careful when you run a parallel train job to mix, to properly isolate manually the GPUs. So below there is a screenshot of what it looks like to actually use that process runtime, local process runtime. You only have to basically nothing changed. The only difference is that you have to provide the backend config, and there you provide the local process backend config. There are a few configuration parameters. For example, when you want to troubleshoot your train job, if you run it locally, you can keep around the virtual environment. And also just something to notice is that the parameter where you can specify the number of nodes when you want to distribute the training job is not taken into account because, as I said before, that local process runtime only supports single node training job. So the second one that we've developed for running your train job locally is the container runtime. So that one somewhat alleviates some of the limitation of the local process runtime, in the sense that you can use all the preset and your custom training runtimes. It supports both Docker and Podman container runtime. So whatever is the one that you've installed on your local host. That container runtime support multi-node, so you can distribute your model training locally with GPU support. So just if you use Docker or Podman, you'll have to make sure you have installed the NVIDIA Container Toolkit. One thing to notice, because we've tried, well, at least I've tried it, that if you're on MacBook and you wanted to leverage the Apple Silicon accelerator, the integrated GPU, it's not going to work, for example, if you want to use the PyTorch MPS backend, because it only supports it. There is only a build for Mac, and when you're on Mac, whether it's Podman or Docker, it runs in a virtual machine. So there is no at the moment support for Linux-based PyTorch MPS backend. So for that, if you really want to leverage the GPU, your MacBook integrated GPU, you can still use the local process runtime, and that works perfectly fine. And one thing to notice as well, when you do distributed model or training job, you have one dedicated network with DNS support for each training job. And as in the previous slide, so the only difference that there is when you want to use that container runtime is the backend config parameter, where you have to use the container backend config. And there you can override. So basically, default it tries to auto-detect what container runtime you have installed locally on your machine, but you can still explicitly set it with the container runtime parameter. All right, so that's it also for that second functionality we've introduced in the 0.2 version of the Kubeflow SDK. So as Anya mentioned earlier in some previous slide, at the moment in that version of the Kubeflow SDK, you have the trainer client and you have the optimizer client. So what's in the roadmap in the short term is that we are going to add dedicated client for the other component in the Kubeflow ecosystem, for Kubeflow pipeline, for the Spark operator, the model registry. One thing we plan also to add is the support for the local execution for the optimizer client for doing hyperparameter optimization locally. One thing also that we'd like to focus on is experimentation tracking. So with model registry, but also with some other like experimentation tracking solutions like MLflow and weight and biases. And a functionality also that we plan to add support for is the ability to take a snapshot of your working directory of your local environment and replicate it into Kubernetes, into the distributed node of your training job, so that you can have more complex configuration for your training job. And with that, pass on to Anya.
Thank you. So to address all of these challenges for AI practitioners, we created a dedicated working group in Kubeflow community, which is called Kubeflow SDK and Machine Learning Experience Working Group. So please come and join us. There's lots of work. That's a new project that is growing really fast. Check out our good first issues to start your first contribution. We do have a Slack channel in CNCF Slack, which is called Kubeflow ML Experience. Join us, say hi, ask any questions or provide any feedback you have. We also have meetings which are every Wednesday, bi-weekly meetings, Wednesdays, 3 p.m. UTC time. Come join us and start your contribution. We are looking for new contributors.
And so what you've seen, the demo and all those new functionality, they have been made possible by the many contributors to the Kubeflow SDK, Kubeflow Trainer, Katib, etc. So this is really a great community, and this is one of the best that I've been the opportunity to be part of. So if you haven't joined yet, please join, and we'd be happy to welcome you.
Thank you. Same here. I've been really enjoying being a part of this amazing Kubeflow community, and recommend everyone to join us. Also, before we wrap up, we do have a blog post that we recently have published regarding Kubeflow SDK. There you can find more details about how you can use that, who is it created for, etc. More resources there as well. And then please scan this QR code for Kubeflow SDK survey. We are shaping the future of this project, and we really need your feedback. So if you have time, scan it and provide your feedback. And ask any questions if you have any. And thank you so much for listening to us. Thank you for your attention. And if we have some time, if you have any questions, please ask them now.
Thank you for a good presentation. So we actually create a hassle-free service for end user. And my question is, what about the efficiency control? Do you provide something? I don't care about like selecting proper instance in the different cloud providers. I just want to run, and I want like feedback. Is it efficiency enough? Should I use this instance type over the other? Do you provide something like this? Are you planning to do this?
Right. So if I understand it correctly, when you say instance type is the machine like with certain type of GPUs, etc. Yeah. So at the moment you can configure like the labels and the node selector, etc. to choose the instances that you want a training job to run on. So that's one thing. But I think we can improve that part, the API, to make it more functional or higher level, I think. So we'd be happy maybe to discuss on what you think would be ways to improve the. At the moment, that part to be fully transparent, I feel like it's really probably a bit coupled with the Kubernetes primitive. So ideally, we would find a nice way to. But generally, the approach at the moment is that those kind of details, they are abstracted with the training runtime API. So that's generally something that the platform admin take care of, like configuring all the Kubernetes specifics and then you can as a let's say data scientist or AI practitioner, you only have to know the name of the training runtime, and you should be all set. So that's generally the philosophy, but probably some room for improvement there.
Yeah. Thank you.
Welcome.
Hey, so I just want to say, first of all, kudos. Our users are going to be thrilled about this. And I'm going to be thrilled to not have to help data scientists tie their shoes as much. So I guess I have two questions. One is target state going to be like a centralized repository, or are you going to do like a hub and spoke sort of model where each like sub project maintains their own SDK, but you import it into the central SDK? And then my second question is, have you guys at all thought about like a notebooks SDK?
I can answer the first one. Yeah, so regarding the SDKs, we had a big discussion regarding that. Currently, we are migrating the SDK code base to our one repository. We might consider importing that, but we want to provide the seamless experience for AI practitioners. For example, regarding Katib, we needed to redesign the APIs completely so that it's transparent and aligned with trainer client as well. So you have a seamless experience for AI practitioners. You can just use the same APIs, etc. So before including any SDK as part of the unified SDK, we'll need to redesign completely if that's the case, or make sure that it's aligned with the current approach. Yeah. And then the next question.
So the second question is about an SDK that would like provision notebooks, right? So that's a very good point. At
You're
least,
looking at Andre.
I'm looking at Andre because
What?
Yeah, it's a good question to discuss it, but the goal is to make it easy for AI practitioners. So AI practitioners, they don't want to provision notebooks, they want to use them, right? So that's why it's responsibility for platform managers to do such things, and this is for AI practitioners. So we've been thinking about using this SDK to connect notebook, for example, Slurm or API cluster, like this is what we discussed with Mike, how scientists can have interactive environment and then submit the jobs very quickly rather than just device jobs, making more interactive with API run, for example. There is a way for us to play with this tool, but it's purely for like AI practitioners to make it easy to scale as I was thinking about.
Thank you, Andre. This is our go-to person to ask all the questions.
mastermind.
Yeah, any other questions?
Other quick question is, how do we do observability when we are using this, especially on the hardware, right? I want to see GPU error rates and all this stuff, because there are many ways in which your training can go haphazard if there is a GPU error which happens. How do I correlate all this and have a debuggability where I say, hey, this error happened due to some hardware issue rather than something in my code? How do I do that? Have you guys thought of bringing something together to do this?
What is it exactly? Because
for example, there can be some issue in the GPU memory, right? There can be an error there. And when I'm running a LLM training, my training can go for the toss.
So if I'm just trying, because there are so many ways that can go wrong, basically. But if your question is specifically focused on probably the GPU type of hardware failure, so yeah, that's a very good question. This is something, well, at the moment, like, to be honest, and I'll let Andre and the other like correct me if I may say, it's not really something we have been trying to address at that level. It's more like the functional error, like the application level error. But it's true, for example, at Red Hat and IBM, where they run like very large scale distributed training. And there have been many studies like that shows that whenever you try to scale, like the likelihood that you have such a failure is probably nearing 1. But generally it's a separate component that like is deployed, as Demon said, that runs some probes to try it, because generally those errors oftentimes can be very difficult to narrow, or it can be a bit silenced, like the memory issues, etc. So yeah, it's not, I think, in the scope of the Kubeflow SDK as it is today. Yeah.
I'm just trying to say how to debug my environment, but I want to see if it's my code.
Oh, okay. Okay.
Yeah, sorry, like I think we'll also think about OpenTelemetry integration. like
Yeah.
telemetry for like observability, etc. And also maybe it's about SSH, right? Like about debugging GPUs. Sometimes it's hard for scientists to do such things, but like give them a way to SSH to the node.
So, for example, one of the common things they ask is how do I do NVIDIA SMI?
Yeah,
exactly.
How do I do
Yeah.
that? Right?
So that's the type of thing. Actually, there are some operator that automate the call of NVIDIA SMI and do some like health check on the GPUs and somewhat are collected in a central place in the dashboard.
Is there some work?
Yeah, that's like we discussed this actually. Happy to look for it. Yeah.
Awesome. Thank you. Oh, feedback.
Yeah. Thank you so much
Thank
for your
you.
attention. If you have any feedback, reach out to us. We'll be here or just use the SDK survey. Thank you so much.